Hi, and welcome back. In Module 29, we're going to introduce fatigue failure. So today's going to be a quick overview of what fatigue is in engineering terms. The learning outcomes for today's module is I'd like for you to understand the difference between fatigue and static failure, to understand the dangers of fatigue failure, and to understand the situations when fatigue failure is a risk. So let's get started. Static loading is constant over time, so it does not vary in direction, in magnitude, or in point of application over time. Where fatigue, the loading or stresses are going to vary with time. You'll see words such as cyclic, alternating, fluctuating, variable, repeated, or dynamic. Those are all indications that you're dealing with a fatigue problem. In fatigue, the load or the stresses could vary in magnitude, in point of application, or in direction. And so a good example is to the left we have a photo of the Golden Gate Bridge, and if there are no wind, the weight of the bridge on its supports would be a static load. Now, the cars traveling over the bridge, that's more of a cyclic load, so you'd start to see fatigue failures due to that. Another good example is the engine shown here. It's a diesel engine, and the rotations throughout the engine, the different loadings, the different cyclings, that's all fatigue problems. So you see a lot of fatigue failures in engines. So we've pretty much gone over static failure theory, especially on von Mises's theory and Coulomb-Moore theory, and now we're going to get into fatigue failure theory. So there are very different failure mechanisms, and you always need to understand if your loading is static or if it's, alternating or a fatigue loading situation. So for static loading situations, you get this deformation or this yield that occurs right before the failure if you're in a ductile material. Typically you're failing at the yield strength, or for a brittle material at the ultimate strength. And the theory is well understood, which means that it's somewhat simple to predict static failure, or it's easier to predict static failure. For fatigue failure, it doesn't matter if you have a brittle material or a ductile material. The failure is going to be sudden and it will be catastrophic. It's also going to occur below the yield strength. Fatigue phenomenons are very complex. There's a high variation in fatigue failure from part to part, and therefore it's much more difficult to predict when a part will fail in fatigue. So on the bottom here, you can see a picture of a valve spring. It's a Ford valve spring. And you can see at the fracture site, there's absolutely no plastic deformation. And this is a metal, so it's most likely a ductile material, but you just see a fracture with no plastic deformation. This is a fatigue failure, and it would have occurred quite rapidly. The essence of fatigue failure is occurring by crack propagation. So that's the mechanism, is the part is failing due to the propagation of cracks, which leads to fracture. There's a couple of stages. So stage one in fatigue failure is crack nucleation, and that is in any material or component you're going to have these natural flaws. They could be inclusions, they could be imperfections or voids, but there's these natural flaws, and at these flaws you're going to get stress concentrating. And you're going to get very highly localized yielding at these flaws. That localized yielding leads to slip occurring along the boundaries, which over time adds up and forms microcracks. So most parts will spend 80 to 90% of their life in this stage one fatigue failure. Once you have microcracks, you can move into stage two fatigue failure, which is crack propagation. And this is when the crack spreads throughout the part. It's a relatively orderly growth. Most parts spend about 5 to 8% of their life in stage two fatigue. Now, stage three fatigue, this is unstable crack growth. So it happens when the material remaining in the part cannot support the stress, and you get this incredibly rapid fracture. That's what you would see or hear if a part failed in front of you. You'd see this unstable crack growth. This is a relatively quick phenomenon, and parts could spend 2% or less of their life in this stage. So on the right, on the left, you can see the valve spring, and you can see the fracture sites. There's some SEM photos of the actual fracture site, and if you look, you can see the inclusion that would have caused the highly localized yielding. So this is where the stress concentrated, and it's where the failure and the fracture began. So fatigue, it initiates at discontinuities. These discontinuities could be due to material composition and processing errors, so voids, inclusions. They could be cross-sectional areas that are changing, such as diameters or keys or holes, scratches, tool marks, assembly errors. All of these things can lead to these areas where stress will concentrate and start the initiation of cracking. Also, in rolling and sliding contact, you get these highly localized, concentrated stresses at the point of contact, and that can be another place where you get a crack initiation. So where you start to worry about fatigue is, again, any type of alternating or variation in load, whether it's the magnitude, the direction, or the point of application. It could be an axial bending or torsional load. They could be combined loading situations. And there's also thermomechanical fatigue situations where your part is seeing high thermal fluctuations, which can lead to fatigue failure. So next time, we're going to quantify fatigue a little bit more. I'll see you next module.